So thanks everyone for coming to Qiyuan. This is the fun today. Qiyuan is one of my very first PhD students. He joined the lab in, I think, fall of 2017. And over the last 5 years, he has been a very nice work on snake and snake robot locomotion. So, I'll let you talk more about his research, but I just want to say a few words about my personal impression. So even when he was interviewing, Qiyuan had struck me as being very independent and he would have his own aspirations. He underwent several projects on snake, like robots in various applications. And interview as well as first year working with him, I very confirmed the discussion that he had with the line of inquiry, which quite new at the time. I personally had no experience working with robots before I started the lab year, and he joined in the second year. So he has really driven much of the inquiry, especially in terms of developing, like learning the literature and developing robots, synthesizing what people has done in robot literature, and what I'm focused on is to leverage his strength and respect, which I don't have is myself, and thinking more to become a scientist, using strength to build robots to on these radical requirements to study snake robot locomotion. So Qiyuan has over the last few years published 2 journal papers as first author, and as another one in review. He has also collaborated on a few papers. More recently, in the last couple of years, he has really helped me even explore new research directions by performing a lot of even though he's still a student, he has already been recognized field. Reviewed paper or conference paper. So that I think he has been an amazing lab member, being a more junior student. I've worked with him. I think we're a lot on this solution. Recently, I'm very happy that he got a postdoc offer to work with Propulsion and PPL. I'm especially proud because this position from Qiyuan told me really requires someone who can build a really robust robot and then use it to perform scientific research. Qiyuan really thought it was the top of 20 applicants of his own. So as you guys know, I don't really have expertise to train students to build the best robot. I think Qiyuan himself can really develop that expertise while learning to do scientific research. Anyway, so that's
thanks for introducing and thanks for this mentoring. I'll put all my acknowledgements near the end as well. So and also thanks everyone for coming here. And today I will defend my dissertation entitled "Snake and Snake Robot Locomotion in Complex 3D Terrain." So the reason we study snakes is because they are excellent locomotors in almost all types of complex 3D environments. And because of this, snake robots are very promising platforms to perform critical applications in these complex 3D environments, such as search and rescue, building inspection, environmental monitoring, or extraterrestrial exploration. Their locomotion on smooth flat surfaces have been well studied. The most famous type is called electron undulation. The snake simply propagates a traveling wave down the body to move forward. And the secret to this type of locomotion is a special property called forced anisotropy, in which the forward, for example, on a flat surface, there is a special anisotropic friction between the snake scales and the ground, so that the forward friction is smaller than the lateral and the backward ones. And because of this, the sum of force applied to the snake to the ground by the snake points backward, so that it can move forward while doing this propagation. But they also have other ways to generate this force anisotropy, which I will introduce later. So aside from the lateral undulation, they can also use alternating static contact with the ground to move forward. For example, sidewinding, concertina, or rectilinear. And because of these inspirations, the snake robots can also use similar modes to traverse smooth flat surfaces relatively well. And when there are vertical extrusions available on these flat surfaces, they can additionally utilize them to improve their performance, because they can easily get larger anisotropic force by pushing against these vertical structures. For example, when they are using lateral undulation, they can just push against these vertical paths. And where they are using concertina in a narrow tunnel with two opposing walls, they can brace against these walls for a firmer static contact, and then extend the other part of the body forward to move forward. And because of this, the principles have been well understood and applied to many snake robots that allow the robots to traverse similar environments very well. However, the studies on the snake's 3D terrestrial locomotion are still lacking. Most of the previous studies focus on their terrestrial locomotion on flat surfaces, and the snakes have very little small out-of-plane body deformation, usually used to reduce the friction between the body and the ground. And those that have quantified very large out-of-plane body deformation really is for their arboreal locomotion. And these environments are very different from the terrestrial ones, because there are fewer structures for them to support the body weight, but also more thinner structures for them to grip or wrap around for propulsion or stability. And as for the terrestrial locomotion, there are not so many studies. Because there are only a few from our lab and our collaborator, Henry Estes' lab, that studies how they use their 3D body bending to traverse these kind of environments with large height variation. So because of this lack of understanding, current snake robots are still struggling in this kind of 3D terrain. Most of them use geometric motion planning to dedicate it for specific environments, for example, pipes or ladders, so that they don't have the versatility to traverse other types of environments. And some robots are able to adapt to different terrain using controlled compliance to adapt to the height variations. However, because they are still using the gates designed for flat surfaces for propulsion, you can see that they are still, even the best of them are still experiencing very severe slipping, and it seems that the propulsion is not large enough to overcome the resistance there. And some robots use active propellers, for example, these actuated treads or wheels, to increase the propulsion, which works quite well. But these propellers occupy extra weight and space inside the robot, and also it is very challenging to seal them for them to work in wet or sandy environments. And also, often they are using a simplified follow the leader control strategy, which results in a very narrow base of support that can induce lateral instability. So what does the additional vertical body bending induce when they are traversing in a 3D environments compared to their low 2D locomotion? One point is that because of the central mass is raised up, there is more challenge to maintain stability. And also because a large part of the body is used for vertical bending, if they are still simply relying on lateral bending to provide propulsion, because of the shorter body section, there will be less propulsion generated, and maybe that is not sufficient. So the overall goal of this dissertation is to understand how can the vertical body bending be used stably, and also can it be used for propulsion generation. And to approach this question, we studied both snakes and snake robots, in which we use snake robots as amenable physical models that allows us to test some hypotheses from the observations in animal experiments, while the animals can also inspire the design of the snake robots. And we challenge these models in 3 representative 3D environments: a large smooth step, an uneven terrain made up of blocks of random heights, and also large bumps. All of these 3 have very large height variations. And our first project studies the stability principles during the step traversal. So we challenged the robot to traverse this kind of large smooth step and see how stable it is. And what we found is that the instability increases with the amplitude of vertical body bending. Aside from, we didn't test the control policy for this one, but we found that a passive mechanism of body compliance can increase the stability by improving the contact between the robot and the terrain. And then to better understand how snakes traverse more complex 3D terrain, we tested corn snakes, a generalist snake species that live in a variety of environments, to traverse this kind of uneven 3D terrain. And then we measured their kinematics and their interaction with the terrain. And we found that they can contact the 3D terrain not only from lateral bending as previous snake robots do, but also using the vertical body bending. And there are also strong evidence that both these 2 types of body bending styles can contribute to propulsion by pushing against the terrain surfaces. And finally, to understand how we can use vertical body bending to generate propulsion, we use snake robot as a model and let them traverse these large bumps using vertical body bending only. And we found that by propagating a shape down the body, it can generate sufficient propulsion to accommodate resistance such as friction or other external forces just by pushing against these uneven terrain. And when we add contact feedback control to the robot, it can improve the robustness of this strategy against unexpected perturbations that will cause loss of contact by regaining the lost contact and then maintaining the propulsion and the success rate. And then I will first talk about our first project, which studies the stability principles during the step traversal. And as I mentioned just now, on flat surfaces, the snakes are able to move forward using near 2D body bending, which is inherently stable because of the very low center of mass. But when they use 3D body bending, it will cause some stability challenges, as you can see on this robot using side winding to move up a slope. And in some environments, they are able to maintain stability using anchor points. For example, in arboreal environments, they can grip these horizontal rods for stability. And on this sandy slope, they can push against this depressed sand for stability. But there are also environments where the obstacles are too large and smooth for them to gain such kind of anchor points. For example, over a large boulder or over a fallen tree, but still snakes can traverse this environment. And how do they do that? Our previous limits found that they are able to use a partition gate to traverse this kind of environments. They tested it using king snakes, a kind of generalist snake. And the partition gate is that they can partition the body into 3 sections. The anterior and the posterior sections use lateral undulation on horizontal surfaces for propulsion, and the middle section cantilevers in a vertical plane to bridge the height difference. And when the snake is moving upward, these entire patterns travel down the body. And because of this combination, they have a much wider base of support compared to most of the previous snake robots that have tried traversing similar terrain. This allows them to traverse much faster than the previous snake robots, and also with a 100% stability in all 120 trials. And there are indeed some robots that have tried combining the lateral and the vertical body bending to traverse similar environments, but they are relying on very accurate feedback control to maintain very well contact between the robot and the terrain, even if just for a very low step. Otherwise, they will frequently lose contact with the terrain. And to better understand the stability principles for these kind of locomotors when they're traversing this large smooth step, we developed the robot as a physical model. As I mentioned, this has a benefit of allowing systematical variation of mechanism of interest, for example, the controllers or some other mechanism that we mentioned later. And this allows us to do repeatable experiments and also test environments that the snakes are unwilling to attempt. For example, for very high steps, we can't get the snakes to traverse it. And this also provides direct examples of future application and many other benefits, which recently have resulted in a large number of discoveries about animal locomotion. So for the snake robot we use, it has alternating pitch and yaw joints so that it can bend in 3D. And it is also equipped with one-wheel wheels to produce the anisotropic friction property that is necessary for it to generate propulsion on a flat surface using lateral undulation. So this one has a smaller forward friction compared to backward and lateral ones. And then we applied the partition gate to the robot and using 3 markers to tell the robot about the step height and the distance between the head and the step. And with this gate, the robot is able to climb up a step that is similarly high as those that can be traversed by the animals in our previous experiments. However, when we challenged the robot with an even higher step, we found that the robot fails more often and the traversal probability drops a lot. You can see from the video here, it lost contact with the ground and then rolled to one side, and often, eventually they will flip over and fail. So recall that the snakes can maintain 100% stability during the traversal for every type of environment that our previous lab members tested. So what is still missing here? And one thing that came to our mind is that the snake body is very compliant, but our robot at that time was a rigid body robot. So could this body compliance be an important factor that can improve the performance? And to test it, we added a car-like suspension system between the wheel and the body so that the robot can switch between a rigid body robot or a compliant body robot. Then we compare the performance of the robot with only this change, and all the other like controllers, etc., are the same. And the compliant body robot is able to traverse the same step with a much higher traversal probability. And to really figure out if it is because the body compliance increases stability, we looked into several adversarial events during the traversal. There are 3 types mainly. The first is called rolling. It rolls to one side. Sometimes it can recover, but sometimes it will flip over. And the more this situation happens, the more low instability the robot has. And there are also 2 other events in which it will change its direction or getting stuck or got stuck on the edge. So we plotted the graphs that show the transition between different events. And if you look at the red arrows here, and also the line thickness indicates the probability of the transition. So if you look at the red arrows here, you can see that it becomes thicker for higher steps, which means that for this rigid body robot, the low instability increased with the step height, and also the amplitude of vertical body bending. And I'm going to show the graphs for the compliant body robot. And if you still look at the red arrows here, they become much thinner with the body compliance. So this implies that the body compliance does reduce the roll instability and also the flipping over probability. So in fact, if we look at all the step heights we tested, the body compliance increased the traversal probability by reducing the roll failure probability, which confirmed our hypothesis.
Red is the compliant one?
Yes, red is the compliant and the red. Yeah. And thanks to the partition gate and also the body compliance, our robot achieved better performance than the previous robots. So here, the slope here shows the normalized traversal speed equals to the normalized step height divided by the traversal time. And our robots are here. Although it is still behind the animals, it's faster than most of the robots except this one, which used active wheels to propel it forward and using a narrow base of support, which can have lateral instability. Okay, and then, and also if you have any questions, please feel free to ask.
Remember that part, the compliance?
Yeah.
You added the compliance and improved performance, but you have insight into why?
So we analyze the contact between the robot and the terrain as well, in which the body compliance increase the contact, which means that it can make the support polygon larger, which gives it more stability. That's our explanation. Okay, and then I'll move on to our second project, in which we are interested in how the animals traverse these complex living environments. So, as I mentioned in the beginning, the propulsion can be generated by using by either the kinetic friction or the static friction between the body and the ground when they are on a horizontal surface without any vertical extrusions. And once there are these vertical structures, they can also push against them for a larger normal contact force to move forward. And all this because they are flat surfaces, they do this by using lateral body bending. And inspired by this, many snake robots are able to use lateral body bending to push against obstacles to move forward in similar environments. However, when they're trying to use these strategies on an uneven 3D terrain, they slipped a lot and seems to not generating enough propulsion to move forward. So then we wonder, like, aside from lateral body bending, what can the vertical body bending be used for? And in the previous robots, they are used either to reduce friction, to lift the body off the ground and move laterally, or to connect to propulsive body segments like these two undulating segments. Or a more common way is to use controlled compliance to let the body bend vertically to maintain contact with the ground. But in addition to this, our collaborator Henriette's lab also found that they can generate propulsion by using vertical body bending, just by pushing against these horizontal structures. For example, they measured the reaction forces applied to the snake from this horizontal rod, and they found that there is very little lateral force component, and also the snake is not using the lateral bending much. In contrast, the vertical and the full-out force are very large, and also they can manipulate the force to be propulsive or for braking. Maybe they are coordinating these forces on multiple rods. And similarly, when they are inside a narrow channel, initially they use concertina, as you can see from the little wiggling here, to move forward. But once it gains contact with this triangular block, it no longer uses the concertina and use vertical body bending only to move forward, and is much faster. So in these simple environments, they don't have the lateral structure that they can use lateral bending to push against, except that narrow channel. But For a more complex 3D environment, which have both the lateral structures and the structures below the body, what do they do? Like, do they, like the snake robots before, just use lateral body bending, or do they also use vertical bending a lot? So to understand this question, we constructed an arena, which is constructed by these low friction acrylic blocks, so that it's not very likely for them to use the lateral undulation to use the force and so anisotropic force, because we measure the friction and the anisotropy was not very significant. And then the height of the block of each block follows a normal distribution and is randomly distributed around the terrain. And we attach markers to each block and use 12 cameras to track them so that we know the 3D position and geometry of these blocks. And then we put constant inside and track their kinematics. And to track the continuous kinematics of the entire snake, we use the custom method that has a higher accuracy than the commonly used B-spline method. And to do so, we first attach these small beta markers to the snake. And then we first got the 3D position and orientation of each marker. And then for each body section in between two markers, we simplify it as an elastic rod subject to the end constraints from these markers. And then we can interpolate the continuous body in between. So first, we found that they are doing amazingly well in this terrain, even if the friction is very low, and also it's a complex 3D environments. So they do so by propagating a shape down the body as if moving a virtual tube, and the slipping angle was as small as 14 degrees. And despite we have the kinematics, how are they interacting with the terrain? We know from previous studies that there are two possibilities of propulsion, that one can come from lateral body bending to push against these lateral structures, and also it can come from vertical body bending to push against these vertical structures. So in these 3D environments with both lateral and vertical structures, do they prefer one of each over another? So to understand this, at that time we don't have the force sensor to distribute it around the entire arena. So instead, we use the kinematic data to infer how the body is interacting with the terrain. So to do so, we reconstructed the body surface of the snake and then see how it interacts with the terrain blocks below and around the body. And from the kinematics, we know we can classify several types of body terrain contact. And the simplest case is that they are not contacting any terrain and not likely to generate any reaction force. And also, they can contact the structures on the lateral side by using lateral body bending. So, and then, for example, pushing against a vertical wall like this, or pushing against a vertical edge like that. And we further assume the direction of the reaction forces. There will be a normal contact force that's normal to this surface, or say we'll assume that it's normal, it has the same angle between these two surfaces. And then there will be a friction, although very small, that is contrast to the local movement direction. And also, it's possible for the body to contact the structures below the body, for example, by sitting on a horizontal surface or by pushing against a horizontal edge. Because the friction was very small, so we are particularly interested in these three types of interactions, in which these two are likely to generate propulsion using lateral body bending to push against horizontal structures, and this one can likely generate propulsion by pushing against these horizontal edges. And we call them lateral contact and vertical contact later. So we found that in some trials, the lateral bending alone may be insufficient. For example, in this trial, there are barely any lateral contact points in this trial marked in blue. And so if the snake is only using lateral bending, it's probably not generating any propulsion. And in fact, we counted the number of these contact regions along the entire body, and averaged it for all the time frames and also in all the trials. We found that the number of contact regions are actually more for vertical body bending than for the lateral body bending. But still, the numbers, they don't necessarily mean they are contributing to propulsion. They may also be used for braking. So we wonder how much do these contact regions really contribute to the propulsion that's aligned with the movement direction. And remember that we just assume the force direction, and we further use them to define these contact regions as potentially propulsive ones or not. So we do that by looking at the angle between the assumed force and the center of mass velocity of the entire snake, which can represent its movement direction. And if the angle is smaller than 90 degrees, we say it's possibly potentially propulsive, so that we can count the number of all these potentially propulsive contact regions along the body, which can somehow indicate the potential of them generating propulsion from lateral or vertical body bending. So, for example, here there are two vertical contact regions that can potentially generate propulsion, and there is one for lateral body bending. And then similarly, we counted the number of these potentially propulsive contact regions, and we found that they are actually similar for both lateral and vertical body bending. So what does this tell us? This means that if the snake is able to combine lateral and vertical body bending for propulsion, they are likely to increase the number of push points available for it to use. For example, they can use them to coordinate forces for either propulsion or for turning or maneuvering, which will give it a lot more redundancy. So, for example, at this moment, if it only uses lateral body bending like previous snake robots, it currently only has one point available, and needs to slip laterally more to get some more points to either to maintain the direction or for larger propulsion. But if it's also able to use these vertical contact points for propulsion, then it has a lot more redundancy in coordinating the force. Okay, and that's all for my second project. If you have any questions. Okay, and then I'll move on to my third project, in which we would like to understand how vertical body bending can really generate propulsion effectively, and also how we can control this vertical body bending, potentially with some feedback control to improve the performance. And snakes are able to use vertical body bending for propulsion, and so do some snake robots, but they are currently lacking the versatility to adapt to different environments, because they are either designed to test it for dedicated environments manually, or need manual control of the heading, or to switch the mode, which is quite important for them to generate sufficient propulsion. And there is only one case in which they can use feedback control to adapt to different terrain, but they derived the model using a very ideal assumption that ignore any longitudinal resistance and gravity. So we would like to know how we can improve the versatility of the vertical body bending when they are generating the propulsion. And we know that snakes are able to use feedback control to modulate their body bending. For example, they can change their patterns based on the spacing of these paths, or based on the random locations of these paths. And also, in a narrow channel with different width, they are able to adjust the bending patterns to adapt to it as well, likely using sensory feedback. And indeed, the principles have been well studied, and people are able to reproduce the traversal of an array of paths using sensory feedback control, using the contact information and also the bending shape information. And then people can apply these strategies to the robots to let them traverse similar environments automatically using these principles. However, the control policy can be different in the vertical plane because on horizontal plane, you mainly need to consider the contact forces between the body and the obstacles. But in the vertical plane, you additionally need to consider gravity, which can significantly affect the performance of the robot. So our question for this project is, when can vertical body bending effectively generate propulsion? And also, how can the feedback control help improve the performance in the vertical plane? And again, to test it, it's not likely for us to test it on snakes because they have very complex structures that have not been well understood yet. So we again used a robophysical model, which can bend in the vertical plane. It has the passive wheels, which reduce the friction and also allows us to install force sensors between the wheels and the body to measure the normal contact force for feedback control. And then we let it traverse a track with large bumps, which produce a large height variation using vertical body bending. And then to understand the control policies, we tested 4 different controllers. And the first one is the simplest feedforward controller that propagates a predetermined shape down the body. This is inspired by that the snake seemingly just propagate the shape without any change down the body. And then we have 2 feedback controllers, which aside from propagate the shape, also controls the head to adapt to the terrain. This is inspired by the observation that the snake seems to move its head laterally and dorsoventrally more as if exploring a path, while the other part of the body simply follows the head. So these 2 controllers are slightly different in the implementation. This blue one senses the contact force at the first wheel and controls the angle of the first joint to try to maintain its force using a key controller. And then the second one is that just constantly pushing downward the head with a constant torque. And for the propagation, they both read the current shape of the body so that they can propagate the shape down the body. But this one uses position control for each joint, which controls the shape. And this one controls the torque instead, which automatically has some ability to conform to different terrain. And then the last controller, we tried use more information from the entire body. Basically, it senses the contact over the entire body and control the body to deform downward to in contact with the ground while propagating the shape down the body. So this is inspired by the observation that sometimes the snake can change its body shape to be different from its head trajectory in some environments that has very large slipping. So then we tested these controllers on the different perturbations to test their performance. The first 3 types of perturbations added different additional backward load using a pulley system, ranges from 0 to 70% of the total friction when it's lying on horizontal ground. And we wanted to use these perturbations to test how large propulsion the robot can generate using different controllers. And then also to simulate their ability to adapt to different environments, we added 2 other perturbations that either let the robot lose important contact with the ground, or just added another unknown bump in front of it to see if it can adapt to it. And for each combination, we collected 5 trials and resulting in 100 trials in total. And here's what we found. First of all, the conditions for vertical body bending to generate large propulsion. First of all, this shape has to be, it can do it by continuously propagating a shape down the body. For example, in this trial, even under a very large backward resistance, it can traverse the entire bump successfully by propagating a shape. But in this trial, because the torque is somehow limited by the controller, so it cannot propagate the entire shape down the body to a stop here and get distorted. So the robot got stuck here even if there is no external load at all. And secondly, this shape has to maintain very good contact with effective vertical push points, basically very steep surfaces that can effectively convert the near normal reaction forces to propulsion. For example, in this trial here, this controller lost contact with the steep surfaces and only can push against these very near flat surfaces and does not have enough propulsion to overcome the resistance here, so that it got stuck halfway in the track. And thirdly, it has to maintain sufficient contact with the ground so that it does not overload the motor. As you can see here, this robot is lifting too long a body section here that installs the motor here and failed. So if we look at all the trials here, these trials in green boxes have very small lift-off height, which means it has very good contact with the ground and also has a high success rate, which means that the trial satisfying these conditions can be successful even under large additional load, for example, this condition 3. And how does contact feedback control help here? As you can see, most of the failure results in loss of contact, which is a common behavior for these feedforward controllers when there are perturbations unexpected. And by sensing the lost contact here, feedback controllers can let the robot to regain the lost contact, and then it can maintain the propulsion and also won't have the issue of model stalling. And finally, if we look at all the trials here, for these 3 especially challenging conditions, the feedforward controller lost more and more contact, and then results in low success rate. And for the feedback controllers, especially the 2 and 3 here, they can reduce the lift-off height, which means that it improves the contact, and then can still maintain a high success rate for all these trials. And finally, as a summary, this project discovers several mechanisms that can affect the performance of this snake-like 3D locomotion, and mostly by affecting the contact between the body and the environment. For example, for the 3D body bending here, the larger the vertical body bending, the more the roll instability. But the vertical body bending can also contribute to propulsion by pushing against the terrain. And for the lateral body bending here, even in 3D environment, snakes are also using them for propulsion by pushing against the terrain. And then by adding contact feedback control, we can improve the performance of these propulsion generation strategies by improving the contact between the body and the terrain. And finally, aside from these control policies, there are also passive mechanisms like body compliance, which can improve the performance, such as stability, by improving the contact between the snake body and the environment. And there are still more to understand for this snake-like 3D locomotion, and it's promising to further integrate this biology, robotics, and these theoretical models to understand them. For example, animal experiments can provide a lot of inspirations for the other 2 aspects, and the robots can provide amenable physical models to test different hypotheses and also to validate these theoretical models. And the theoretical models, they are an abstract explanation of all these complex phenomena observed in animal experiments, and also can guide the design of more efficient robots. As to the animal experiments, as I mentioned, for our second project, we didn't have the force sensors to measure the conditions, to measure the reaction forces. So our findings are based on some assumptions about the geometric interactions. So it will be very helpful to measure the forces directly. For example, we can construct a terrain with each module that can measure the 3D reaction forces. This can help us understand, for example, how does the force change with the body bending, and how the multiple forces on the snake body is coordinated. And then we can also measure the muscle or neural activities to better understand the biomechanics. For example, unlike most snake robots that bend a single joint using one single motor, a snake has muscle groups that span over dozens of joints. So does this structure give it more advantages, or does it have some other purposes? Maybe these experiments can help. And also, it will be helpful to directly measure the neural signals so that we can understand how the snake respond to different feedback. And it will also be interesting to compare snakes with other limitless species, for example, nematodes or eels, which can also use the bending of their elongate body to traverse complex environments. And for the robot, it will be helpful to develop a compliant and continuum robot so that it won't get stuck by different disparities in complex 3D environments like those wheeled ones. This is one that we are developing, which has a rigid skeleton and a compliant shell that can adapt to the terrain, and has compliant force sensor that can measure the contact forces. And we can use them to investigate some problems like how to coordinate the forces in 3D, and whether a decentralized control structure can save the communication bandwidth for faster response, or can these musculoskeletal models inspire some simple mechanisms? For example, this one used bilaterally actuating muscles, which can produce this traversal behavior with a feedforward control. And then finally, we can try to apply them in more complex real-world environments. And also, there are more to work on the theoretic modeling side, which I didn't touch here. For example, like using elastic rod to describe the snake body and to investigate the contact mechanics between the continuous body and the terrain. And also, we can develop models for their neuromechanical structures. For example, there might be different levels in charge of different things, like a central controller to coordinate for high-level tasks, and some local controllers to generate some simple behaviors like the propagation. And also, mechanical properties can be important, as shown in the first project. Maybe the compliance can improve the content, or some one-way mechanism can increase the propulsion. And finally, I would like to thank all the people that contribute to these projects. And first of all, my advisor, Chen Li, for teaching me a lot on how to do rigorous scientific research, and also providing me with a lot of help, not only on research, but also in daily life, especially during the pandemic. And thanks to all my co-authors for contributing substantially to this work, and also providing many insightful suggestions. Thanks to the readers for reading the dissertation and providing feedback, and my lab members for creating a very vibrant atmosphere in the lab to motivate me, and also to provide helpful discussions to improve my work. There are more that I can not include here, and I apologize for that. Oh, and also the funding resources that supported this project. And thanks to the colleagues that provided helpful suggestions to improve our work, especially those at 6B and APS, and to all the course instructors for teaching me the knowledge that I can use for this research, and those who supported my postdoc application. It's a painful process, but I learned a lot from it and get more motivation from it. And to my DQ and GPO committee for examining me and supporting my candidacy, to all the staff that saved me a lot of time and effort to focus on my research, and to my friends who helped me relax and get me out of the struggles during the pandemic, to my cats for their companion, and finally to my parents for their unconditional love and support. And without them, I cannot stand here and defend my dissertation. And that's all, and I'm open.
So, for your third part, talking about local landing, how do you determine the curvature of
So it would be great if I can make them arbitrary. So one consideration is that because I'm using the wheels, so I'm trying to, and also to sense the contact forces between the wheels and the body. So I'm trying to avoid any sharp asperities that directly contact the servo motors so that I cannot detect the forces there. So that's why it's almost smooth. And hopefully in the future, we can solve this problem with that continuum robot that DVR developed. And another consideration is I want to make this experiment repeatable. So I'm using the same structures for all the experiments, but I'm also considering maybe we can construct some random structures just as a demo or in the future for more rigorous experiments. Thanks for the question.
Very nice one. I have a question about the second part.
Yes.
And even there's a thing first to like observe the surroundings and the environment, see vision happening, is the electrical balance to the monster itself and then to go to the other direction. Or it was just the environment choose to act.
Oh, yeah, that's a very good question. And I think I can show you the video here. Oh, it crashed. Hold on, let me show you the video here. So indeed, in our experiments, we observed that the snakes move its head more laterally and dorsally more, as if it's exploring a path. And after the head, most of the body simply follows the path generated by the head. And I will show you the video once it launched. So and also we calculated the sleeping angle for the head region and also for the other part of the body. And we found that the head moves, the sleeping angle is significantly larger for the head, which also indicates a potential exploration behavior. But because we cannot measure the neural signals in the animals, so we are not able to directly test that. So maybe that's why we added a controller to test it in the experiments. And yeah, here's a video. As you can see, the head does move a lot more to the side, to lateral side, and also dorsally as if exploring. Any other question? Or from the online audience? Okay, and if not, you're always welcome to email me your questions, which is available on our website. And again, thanks everyone for coming. And that's all for today's defense.
Which I'm again, we're going now to step out.